So now let's discuss different fundamental types of lattices. Crystal lattices can be mapped into themselves by various symmetry operations, and that makes different fundamental types of lattices. The first kind of symmetry operation that is a must for every crystal is translation. So if we translate one atom, one lattice point to using this kind of a relationship, translation of u1 a1 plus u2 a2 plus u3 a3, where u1 u2 and u3 are integers, this will find a similar kind of point. So this kind of translation would map the crystal itself, map to the crystal itself. So we will have every solid structure that is symmetric to this kind of, that is invariant to this kind of an operation, that is translation. There are other symmetry operations often in a lattice. Rotation about an axis that passes through a lattice point, that could be an operation. So in lattices we can find one-fold, two-fold, three-fold, four-fold, or six-fold rotation operations possible that maps the crystal to itself. So the associated rotation angles are, for one fold it is 2 pi, for two fold it is 2 pi over 2, that is pi, for three fold 2 pi over 3, four fold is 2 pi over 4, that is pi over 2, and for six fold it is 2 pi over 6, that is nothing but pi over 3. We cannot find a lattice that goes into itself under other rotations. If we have 2 pi over 7 or 2 pi over 5, these kind of rotation angles, we won't map the lattice to itself in that kind of an operation. While it is possible for a molecule to have any degree of rotational symmetry, and you are familiar with it, an infinite periodic lattice cannot have that. So try disproving this statement by drawing pictures, imagining it yourself, looking at the computer screen, whatever way you like, and you will appreciate this statement better. Okay, now let's move on to different lattice systems in 2 dimension. This is for simplicity. Our world is 3-dimensional, so we will have to learn about 3-dimensional lattices. So there are 5 different types of lattice in 2 dimension. These are called Bravais lattices. The first one is, there is no symmetry. So in 2-dimensional case, we will have 2 lattice vectors, a1 and a2. So a1 and a2 are not equal, and the angle between them is also arbitrary. That's the least symmetric situation. And there are spatial lattices, that means more symmetric situation than the first one. Those could be square lattice, for example. How do we have a square lattice? We will find a square like this. doesn't really look like a square, so maybe I modify the picture a bit. I draw this up to here, and that gives me a square. The corners are lattice points, and this vector is say a1, this vector is a2, and the angle between them is phi. So in the case of a square lattice, we have the magnitude of a1 equals the magnitude of a2 obviously, and the phi angle is 90 degree. That defines a square lattice. We can have hexagonal lattice in 2 dimensions. How would a hexagonal lattice look? An atom at the center of the hexagon, then a lattice site at the center of the hexagon, not atom, and similarly one here, one here, one here, one here. Repetition of this will make a hexagonal lattice. We can have lattice vectors like this and this, and this will give us, as you can see from this picture, a1 equals a2, and this angle here phi. For a regular hexagon, this angle would be 120 degree. We can also represent hexagonal lattice like this. Say we have a1 drawn like this, a2 drawn like this. This is not a different picture, although the angle is different. It's exactly similar kind of a representation. And we can have rectangular lattice certainly. As the name suggests, we will have a1 not equals a2, and the angle phi would be 90 degree. If we draw it, we will have something like this. With the lattice points at the corners. This is a1, this is a2, and this thing repeated. That will give us a rectangular lattice. We can also have centered rectangular lattice. Centered rectangular lattice is something like this. Say we have a lattice site here, one lattice site here, one here, one here, and one here. We draw one vector a1 like this, another lattice vector a2 like this. Here this is a centered hexagonal, centered rectangular lattice, where at the center of the rectangle there is one lattice site. So this, you can clearly see, is not a primitive lattice, because there are more than one lattice sites in the unit cell that we have considered. So it's not a primitive unit cell. How about we move on to 3-dimensional lattice types? Let's see how it goes there. We can have 14 different lattice types in 3 dimensions. These are called Bravais lattices. Out of these 14, one is the least symmetric one, and 13 special lattice types. Let's tabulate these things. So we will write it, we will make a table like this. The system, then we will put the number of such lattices. Then its attributes. If we try to classify lattices in this way, then the first thing that comes is triclinic. That's the least symmetric one, and there is only one type of lattice. Its attributes are, because it's the least symmetric one, A1 not equals A2 not equals A3, and the angles between these lattice vectors alpha, beta and gamma, they are all different. Alpha not equals beta not equals gamma. Then a little bit higher symmetry is monoclinic. Two such lattices are possible, and its attributes are all the lattice vectors are of different length. A1 not equals A2 not equals A3, but we have alpha equals gamma equals 90 degree, while beta is not equals 90 degree. The next one is orthorhombic. There can be 4 different types of orthorhombic lattices. Here we have A1 not equals A2 not equals A3, but all the angles are 90 degree. Then comes tetragonal. In tetragonal, we can have 2 lattice types, and its attributes are A1 equals A2, but that's not equal to A3, and the angles are 90 degree. So we are moving higher up in the symmetry ladder. Then comes the cubic. Cubic has 3 variants. We will discuss all 3 variants of cubic, although we won't discuss the variants of other lattice types. You can find it out over internet if you are curious, or because those are more clumsy, we will avoid discussing that here. For cubic, it's obvious that A1 equals A2 equals A3, and all the angles are 90 degree indeed. After cubic, we go to trigonal. There is only one type, and here the attributes are A1 equals A2 equals A3, and the angles alpha equals beta equals gamma, but none of the angles are 90 degree. It's less than 120 degree, not equals 90 degree. And the last one is hexagonal. Only one type of hexagonal is possible. Here A1 and A2 are equal, A3 is different, alpha and beta are 90 degree, gamma equals 120 degree. So here we have defined different Bravais lattices for three-dimensional structure. After defining this, let's see a few examples. More specifically, we want to see the three examples of cubic lattice structures. That will be very instructive. So, the first kind of cubic lattice is called simple cubic. As the name suggests, it's really simple. You have to draw just a cube like this. And at each corner there is a lattice site. This is the simple cubic structure. So can you find out how many lattice points are inside the cell, in this cubic cell? So you can see that if we have a sphere at each corner, only 1/8 of that sphere would be inside this cube. That means there are 8 corners and each corner has 1/8 of a lattice site. So in total there is only one lattice site inside this cube. And how many nearest neighbors do we have? Okay, if we count the nearest neighbors here, we can take this lattice site for example, and we can see that it's 1, 2, 3 equidistant points, and similarly we can extrapolate to one below, one behind, and one at the left. So there would be 6 nearest neighbors of this lattice site. Okay, and the lattice vector for simple cubic, the set of lattice vectors is very simple. You can just write A1 equals A, that is the lattice constant, along the x cap direction, A2, that is A y cap, and A3 equals A z cap. It's so simple. These are the lattice vectors. Now let's move on to body-centered cubic. It's called BCC. Okay, how do we draw a body-centered cubic structure? Let's try something similar. Let's first draw a cube. And of course, at each corner we will have a lattice site just like the simple cubic one. What is additional here, as the name suggests, at the center of the body we will have a lattice site. Let's try to draw it a bit better. Maybe it will come somewhere here. At the center of this cube we will have a lattice site. That makes it a body-centered cubic structure. So now you are supposed to find how many lattice points are inside the cell. and it's your homework. And also count the nearest neighbors. Okay, now let's consider the lattice vectors. The lattice vectors, well, you can clearly see that this BCC is not a primitive cell. If we talk about, so this kind of a cell, BCC, which is symmetrically cubic, but the primitive cell is something different that has a lower symmetry. We can represent it as a cube, and then the lattice vectors would be exactly similar like the simple cubic one. But if we want to find the primitive lattice vectors of this, then the primitive lattice vectors would be different from that of simple cubic. The primitive lattice vectors in this context would be it's half A. A is the lattice constant. And A3 equals half A x cap plus y cap minus z cap. These are the primitive lattice vectors in case of BCC structure, and your work is to verify this by repeating this unit cell, drawing a picture, imagining it whichever way you want. Okay, after discussing the primitive unit cell for BCC, let's move on to the face-centered cubic structure. It's called FCC. Let's first draw a structure. Obviously, the corner makes lattice points. And as the name suggests, we will have other lattice points at the centers of the faces. Bottom face, top face, side faces, and front and rear face. All these are lattice sides. When we have this kind of a structure, now again, similar to earlier, your homework is to find the number of lattice points inside the inside this unit cell, and also find the number of nearest neighbors. After finding this, I am giving you the lattice vectors corresponding to the primitive unit cell in this context. You need to verify that. For the primitive unit cell, that is the primitive lattice vectors, we can write here in case of FCC, A1 is given as half A x cap plus y cap. A2 is given as half A y cap plus z cap, and A3 is given as half A z cap plus x cap. So you can see that FCC is also not a primitive unit cell. The primitive unit cell is smaller than this conventional cubic cell. Now I ask you to perform another task, that is find out the volume of the unit cell the primitive unit cell. For BCC and for FCC. This is also another homework. You know how to find the volume of a cell. It's just a triple product, scalar triple product, A1 dot A2 cross A3. That will give you the triple product, that will give you the cell volume, and you need to find this cell volume and compare with the simple cubic one. That's the task. So here we have discussed about different Bravais lattices, and we have carefully analyzed the cubic lattices. There are three possible cubic lattices. One is simple cubic, that's as the name suggests is pretty simple. Body centered cubic and face centered cubic. We have learned its structure, and you need to work out some of these problems that we have discussed to understand to generate a feeling of yourself about the crystal structure.